Welcome back to another video, and today we're going to be talking about how functions work. So you might have heard that term in Algebra 1, Geometry, and Algebra 2. It's something that we use throughout mathematics always. And the thing is with functions is that there's a few tests that we need to do for them. So as we get into functions, you guys can pause the video anywhere, and if you need something to jot down, right, jot it down. But what is a function, right? It is something that we've heard from Algebra 1, Geometry, and Algebra 2, and all of those years that we've heard it, maybe we don't even understand it properly, right? So the definition of a function is it's an input to output device that assigns to each argument in the domain to one and only one value in the range. So what does that actually mean, right? So the thing is, let's say that we're going to break this down, right? So every for every x value, right, there's always going to be a y value for it, right? Now you can still have two x values that has the same y value, right? That is still called a function, right? So we can say that a function is when each x value there is a y value. Now, just from that definition, it's a bit sketchy, but we have some exceptions, right? So we have some like requirements basically. So our first requirement says that for every y value, there could be multiple x values, right? But for each x value, you can't have two y values. So you cannot have multiple y values for one x value. Now, later on, we're going to see how that goes inside the mix because we have something called a vertical line test, which we'll talk about in a few moments here. But how can we actually tell if a function is actually a function or not, right? So there's a few notation forms that we usually use, and our first one is called the map notation. Hence, by its name, we usually do like a little map there, right? So let's say we have a circle full of 4, 5, -2, and -3, right? This is our little block here, right? And remember, this is for the x values, right? So we're gonna write x on the bottom. And then for our y values, we have 5, 7, 10, and 15, right? Now, if I just draw a few lines here, right? There we go. So we can tell that this is a function because it satisfies what requirements we have, right? So for each x value, there is only one y value, right? And there is no multiple y values for one x value, so we are in the clear, right? Now, what would not be correct, as I'm going to draw in the I'm going to draw in the red, right? It can't have, like, let's say we have 4 and 5, right? And then it has 4 and 7. That does not work, right? Because you're having multiple y values for each of the x values that you have, right? That would not work. Now, second notation, we have an ordered pair, right? So, ordered pair. It's like a set, right? So, what we usually name as set is using the variable s, right? So, s is going to be equal to, you're going to have the curly brackets, and then of course, you're going to have your coordinates and whatever, and then you end it off with curly brackets as well. In this notation form, we usually use it for a lot more things, right? So later on, once you get more advanced inside Algebra 2 or Algebra 1, you're going to find it appearing more and more, right? So now, an example that we can have, right? I'm going to draw this in blue. An example that we can have is like s equals curly brackets, and then our coordinates of -2, 8, -1, 1, right? This is what we can call an ordered pair, right? And based off of this, it's a function because for each x value, there is a certain y value, right? So that's that. And we have two more to go. And our next one, right, is a formula basically, right? So formula. Now, in the past, right, you guys use y equals blah blah blah, right? But in this case, since we're getting more advanced, we use something called f of x, right? So now it doesn't always have to be f of x. You can have g of x, you can have h of x, right? It just means that f of x just means y, right? So it looks like this: f parentheses x and closing parentheses. Now you say this as f of x, right? It could also be g of x, right? G of x. We use it to signify the different functions that we have. So as an example function that we can have, right? I'm gonna write it next to the formula. Example that we can have is just like f of x is equal to x squared, right? So now, if you're going to try and figure out like, oh, let's say the x value is whatever, right? Like the x value is 5, right? Now you just need to plug in that 5 to the function that it's supposed to be stated as, right? So in this case, the example that we have here, the function is x squared. So let's say you want to find f of 5, right? Then you just do f of 5 equals 5 squared, because the original function was just x squared, right? So, and then 5 squared equals 25, which is just evaluating the function. Now, lastly, we have something called a graph, right? So graph is just a visual representation, just like what a map is, right? But it tells you more. So a lot of times we do our tests on graphs. So let's say we have x squared plus 1, right? Now, that is what a graph looks like, and by the way, you can tell that for every x value, there is one or more y values here. I mean, no, for every y value, there is more than one x value. We can't say that for every x value, there's more than one y value, since that isn't called a function anymore, right? So now, you might have heard me say domain and range, right? So what is actually domain and range? It might be some terms that you haven't heard of before, right? So we're gonna get that cleared out right away. So a domain is just the x values. And then the range here, and you might have guessed it, the y values, right? So whenever a problem or like a little textbook problem tells you, hey, find the domain from 5 to 7, right? So that you understand, okay, we're talking about the x values 5 to 7, right? let's say it asks for the range of 5 to 7, right? Then you would just find the y values from 5 to 7. So that's what it usually means, right? So domain is the x, range is the y. Okay, now it works a little bit differently in physics. So physics, do not worry about how things are said because they tend to swap things a little bit and it gets a little bit confusing with it. So you might be asking, how can we actually like have a test to see if the function that we have is an actual function or not, right? So we have something called the vertical line test. Now, the vertical line test. Right, so the vertical line test is just to determine if the graph that you have is a function or not. Now, let's draw a graph here because we're going to need this graph for representation of it. Let's say this was our function, right? So the way how this works, right, is that you're going to have lines parallel to the y-axis, right? Hence why it's called the vertical line test. All the lines that you'll be putting down is going to be vertical, right? So we're going to draw some vertical lines here, right? Right, so I'm going to draw with blue here. There we go. My lines are a bit crooked, but if you visualize this, then it's not going to be crooked. So, alright, so we have our vertical lines drawn here, right? So now we can tell that for every x value that we have, right, there is only one y value. So in this case, it means that this is an actual function, right? A case where it would not work would be like a circle graph, right? So let's say the graph of a circle, right? And then I draw vertical lines, right? Bada bing, bada boom. Right. So now in this case, the only issue that we really have is that for one of them, well, for multiple, you see how it crosses the function twice? The vertical line crosses the function twice. So it means that this isn't a function, right? Even though by whatever the equation might be, because for a circle, an equation would be f of x equals x squared plus y squared, right? And even though this might look like, that's really incorrect. Well, a function, right, was x squared plus y squared. That is the function of a circle, right? But the thing is, it looks like a totally good one, right? But in reality, it's not a function, right? Because, first of all, it crosses the same x value in two different points. So, and that does not fulfill our requirements here. So, this is why, hence why we have to do the vertical line test to actually figure out, hey, is it a function or not, right? So, now, if we look at other examples, right, we're gonna figure this out. So, I'm gonna draw an example here, and then you tell me if this function is an actual function or not. We're gonna do two examples here. I'm gonna draw these graphs to the best of my ability. I'm not too good at drawing graphs anyways. It wasn't that bad. There we go. Alright, so these are the graphs. Let's do graph A and graph B. So tell me if these are a function using the vertical line test. Alright, hopefully you just figured it out by using the vertical line test. We can say that we're gonna do the vertical line test on A, right? So at the beginning, hey, it's good, right? But then once you move on to here, where we have the loop, ooh, it hits more than 1 point, right? So this would be not a function, right? Now let's take a look at B. Any vertical line that I draw here, right? It only passes it by 1 point, right? So we can say that this is a function. With check mark, of course, right? So that's how we use the way to find out if this is a function or not. Now, earlier we mentioned about function notation, about like f of x, g of x, right? So the whole point is that we just use it as a notation, right? So we call it the function notation. Now, the function notation here, right? The device of like, with the mapping and everything, right? Let's say we have f of x. X is basically just the input. F, however, is just the device, right? The name. Now, it basically gives you have an input and then it gives you an output, right? So let's say like f of 5 equals 25, right? Now 5 here is input and 25 here is just the output, right? So you're inserting a number, but then it's splitting out a whole entire number just because you have something declared as the function here, right? So now we're gonna use set notation and at least try to understand it and figure out how it works, right? So let's say that given f equals 3 comma negative 1, 5 comma 2, and 2 comma negative 3, right? A, find f of 1 equals what? B, f of, well, not f of 1. Um, I meant to say f of 3 equals what? B, f of 5 equals what? And then C, f of 2 equals what? So take a moment here and try to find it, right? Now, since the input that we have here is just the x value, right? So we're gonna look at the singular x values that we have here. So for our first problem, it says f of 3. So we know that 3 is the x value. So we're gonna look onto here with the coordinate system, right? The coordinates always go by x comma y, as we all know, right? So we're looking for 3. Now I see 3 on the first one, and the y value for it is -1. So f of 3 is equal to -1. Now we're gonna do the same for f of 5, right? 5 is the x value here, right? Because it's the input, we're inputting that number in. And by looking at f, we see that 5 is right here. The y value is 2, right? So f of 5 is equal to 2. Now, lastly, we have f of 2, right? We're looking. We see the x value of 2, and of course the output, the y value, is -3. So f of 2 equals -3. Now, just what if I told you that we're trying to find when solve for x, right? We're trying to find x here, where f of x is equal to 2, right? So think about this, right? As like you're reversing everything that you just did. So first we started off with the input, and then we moved on to the output, right? In this case, you're trying to move from the output to the input. So see if you can figure that out by yourselves first. Alright, so hopefully you just figured it out, right? Now we're trying to move from the output to the input, right? So let's label some things out here. So we know that our output is equal to 2, right? So that means that the y value that we're supposed to find is also equal to 2. So by looking over here on this graph, the set notation that we have here, I'm looking and I see a 2 as a y value right there, right? So we know that since the y value is 2, the x value here is 5. So now we know that, hey, whenever f of 5, whenever 2 equals f of x, that means that f of 5 equals 2, right? So now x in this case is just equal to 5. It's that simple, as we're like moving forward and then we're also moving backwards at the same time. So a little bit more practice would definitely help with that. Now, since we just looked at set notation, right? And on a graph, it works the same. You just look at the x value and then you find your y value, right? So on a graph representation, right, it's gonna look something like this. Let's say that this is like this, right? And let's say this point is -2, and this point here is 4, right? And over here, 5, 25. So now, using this graph of f of x, right? We're gonna label the graph as f of x. Find f of -2, and then b, solve for x, where f of x is equal to 25. So take a moment and try to solve this. Remember, it's the same way how we looked at the set notation, just more visually on a graph this time. So see if you can figure that out, and we'll get right back to it. Alright, so hopefully you just looked at it, right? And try to solve it out. So f of negative 2, right? We know that negative 2 is the input here, so we know that it's x, right? So we're gonna have to look at this x-axis right here, from here all the way to here, right? And we see, hey, I see a negative 2 here, right? So we're gonna go up along this all the way to whatever point the graph leads to, right? And then we're gonna look at the y value here. Oh, the y value is 4, right? So that means that we know that the input, since the input is negative 2, the output has to be 4, right? So f of negative 2 equals 4, right? Now, let's take a look at b, right? Now we're trying to move backwards. So we're trying to move from output to input, right? So our output here, output, is just equal to 25, right? So what can the x value be if our output's 25? So since our output is basically just the y value, now I'm gonna label this in red. We're gonna move from here, from here, all the way up here, right? We're gonna look. So I'm moving up right now, and oh, I see a 4, but we want an output of 25, right? So we're gonna move a little bit more up here, and we see an output of 25. Ooh, that's a good one, right? So we're gonna trace it back to where it started, where the point is, and we're gonna take a look at its x value, right? The x value here is 5. So now we know that the x value is 5. So if we ever said, oh, what is f of 5, right? We know, hey, it's 25, right? So that's how it works. So now, for our last part, right? Last part of function notation examplers, we have a actual like variable function. So let's say our function f of x is 5x plus 2, right? Now we want to find what f of negative 2 is, and then at the same time we want to find uh what is solve for x, right? Solve for x where f of x is equal to 12, right? So take a moment by yourselves, see how you would do this, and this time it works a little bit differently because you're working with more of the numbers here. So be careful of, what you write down and computate. Alright, so hopefully you just looked at it, and by the means of this, right? So our input here is negative 2 for a, right? So since our input is negative 2, we can just plug this into the x here, right? So this would be equal to 5 times negative 2 plus 2. Now, just for your information, we're gonna use a lot of the parentheses here because the main issue that some kids mess up on is just having the negative signs, right? So, of course, yes, you can write it this way. You can write it this way where you have the 5 and then the dot and then the negative 2, right? Or you can just write 5 times the negative 2, right? But it looks a bit confusing when you have variables in here because for this upper portion where you have the x, the multiplication times symbol, right? It looks like the variable, right? Looks like the variable, right? So we don't want to use that notation. But then over here, right? Over here, this dot, even though it serves its purpose, right? But sometimes you'll miss it, right? So when you're reading it and then everything's like that, you're trying to do some fast math here, you're gonna miss it, right? Sometimes I do too. So this is why I like to keep parentheses there, just because it's something that I won't forget, and also it doesn't really make that much of a difference, but whenever you're reading it, it's not missable, right? So, alright, coming back to computing this, right? 5 times a negative 2, that is just negative 10, right? So negative 10 plus a 2, right? And our answer would be negative 8. So now you might ask me, how do we solve number B, right? Now remember, we're working from we're working from output to input, right? So since we know that 12 is equal to f of x, right? 12 equals f of x, right? Well, let's write it the other way around. F of x equals 12. And since we know that, hey, f of x is equal to 5x plus 2, so why don't we just plug in f of x, right? That's the smartest idea that we could ever have here. So let's plug at it. So 5x plus 2 is equal to 12, right? So this is our function that we originally had, and this is the output, right? So I'm gonna box the output right now, and I'm gonna tell you the reason why in a minute. So our function is fx plus 2, 5x plus 2, right? So now we just substituted that in replacement of f of x, because there is no way that we can do any operation without subbing it in, right? Because then you have like minus 12 and it doesn't change anything, right? So now this is a perfect example of how sometimes we would do roots as well, which comes on later on, right? But it's still around the basis of functions, right? So let's try to solve this here. So we're gonna minus 2 on both sides, right? That just equals to 5x equals 10. And of course we're gonna divide the 5 just to isolate x, because that's what we want to find, right? So now on the side we're gonna write x is equal to 10 over 5 is just 2. So in this case, x is equal to 2. However, if you want, we could check it, right? So we're gonna check it in this case just so that we can see how it actually works, right? So in what we just solved out here, it's telling us that, hey, f of 2 is just equal to 12, right? The input is 2 and the output is 12. So now we want to check that. So how would we check it, right? So f of x equals 5x plus 2 plus 2. Now, since we know that, hey, we can just plug in x, right? So f of 2 is just going to be equal to 5 times 2 plus 2, right? And 5 times 2 equals 10. So 10 plus 2, right? And 10 plus 2 is just equal to 12. And 12 is our output. That's our y value. So now we look back onto the original equation, right? Where it says b, right? And it says f of x equals 12. So we definitely know that, hey, you know what? X is equal to 2 here. And it makes total sense here. So that is how we would solve this. Now, by me mentioning roots, right? Roots is basically just how you find the zeros. So it's whenever it crosses the x-axis, right? Now, you use the same way, just that in this case you set it to 0, because when you cross the x-axis, your y value turns to 0, and then it goes negative. Or the other way around, where you come from the negative, you go towards 0, and then you go past 0 to the positives, right? So there's a lot of connection between doing like function notation and everything else in mathematics here. So hopefully you learned a lot today. And even though this is the basics, well, there's going to be a lot more to learn in the future. So make sure you keep on practicing solving function notations based on graphs, set notation, and the maps that we've shown. And make sure that you keep on practicing. And I will see you in the next video.